say that, I feel like at the start of every video, just to get us pumped, get us hyped. Here we go. Integration using U-substitution. What that means, or what that's going to deal with, is chain rule. What happens if our function has a function inside of it? I can hear someone cleaning in the hallway and it was weird sounding. So if you hear it, it's just the acoustics and the environment of a school. Okay, so we're starting off with a reminder of how we do chain rule and why we need this U-substitution when we're doing our antiderivatives. If I take the derivative of the tangent of 6x minus 2, remember we take the derivative of the outside function, so the derivative of tangent is secant squared, and then I keep my inside function. And then with the chain rule, I'm going to multiply by the inside of this, so the derivative of 6x minus 2 is 6. So the derivative here is 6 secant squared of 6x minus 2. So we're going to see the derivative of the inside, right? If you remember, we set this up as saying the derivative of the tangent of u is going to be the tangent of u du, derivative of the inside function. Keeping that in mind, we're going to go ahead and look at some of these antiderivatives, and we're going to have to use a U-substitution because there is a function inside of a function. So for starters, here, I have a function, 3x plus 2, inside my sine function. If I were to have taken the derivative, I should see the derivative of 3x plus 2 here, but I don't. So somehow we're going to have to counterbalance that so we can anti-derive. So let's take a look. I'm going to go ahead and assign my u to be 3x plus 2. And just like with chain rule, I'm going to need my du, so I'm going to go ahead and take the derivative of u, which is going to be 3, and I'm going to call that 3 dx. If you think back to implicit differentiation, here I'm showing I took the derivative of u, and here I'm showing I took the derivative of x. Because we're going to be changing variables with the u substitution, we need to keep track of that. So I'm going to go ahead and I'm going to start making my substitution. Here, I know that u equals 3x plus 2. So that's going to become the sine of u. And I need to replace my dx with my du. Here, I only have a 1 dx, but I need a 3 dx. To be able to make this substitution, I need these to match. So what I'm going to do is I'm going to come in and I'm going to multiply by 3, so I get 3 dx. But now I've just changed my function. So to balance that, I'm going to come in and I'm going to multiply by this 1/3. So to be able to make my substitution to my du, I had to balance my function with this 1/3 du. 3 dx equals du, but since I changed my function, I balanced it with the 1/3 because then I'm multiplying by a fancy 1. 1/3 times 3 is 1. I didn't change my function. And now I can anti-derive. I know the antiderivative of the sine of u. The antiderivative of the sine of u is negative cosine u. When we anti-derive, our integral and our du go away, okay? Du means derivative. Integral is telling us to take the antiderivative. They cancel each other out. So I'm left here, and the last step is I'm going to replace that u with the 3x plus 2. So I'm going to get negative 1/3 cosine of 3x plus 2. Because it's an indefinite integral, we're going to come in and we're going to add that plus c. I almost forgot that. I surprised myself. Okay, the cool thing is these have a built-in checking system. Have I properly taken the antiderivative? Well, go ahead and take the derivative. So I've got my negative 1/3 as a constant. The derivative of cosine is negative sine. Keep the inside. Multiply by the derivative of the inside, which is 3, and the derivative of c is 0, so it's gone. So here, my 3, my negative, and my negative 1/3, those are all going to balance out, and I'm left with the sign of 3x plus 2, which is where I started. Built-in check system, take the derivative. Does it match? Yes, you're good to go. Okay, we've got 2 more examples. If you want to give them a try to see if it makes sense, hit pause, try them, and come back. I'm going to go ahead and work through my next example here. Oh, I forgot to write my dx on this one. That's my bad. So we're going to go ahead and add that here, dx. And now I'm going to start with my antiderivative. So u equals x squared plus 1. So my du equals 2x dx. Here's my x dx, but I'm missing this 2. So I'm going to multiply by 2 and then balance with a 1/2. So now I can go ahead and start my substitutions. 1/2 the integral, the square root of u du. My 2x dx becomes du, and then I replace my x squared plus 1 with u, so I'm here. And now I'm just going to anti-derive. So 1/2, I'm going to add 1 to the exponent, which is 3/2, and then I'm going to multiply by the reciprocal, which is 2/3, or dividing by 3/2, same thing. And then I have my plus c. So my 2's are going to reduce, so I've got 1/3. Substitute back in my x squared plus 1 to the 3/2. And there is my antiderivative. Take the derivative, go ahead and check, make sure it looks good, make sure it works. And I'm okay with what I'm looking at. All right, last one. Here, my function inside my function is my root x, square root of x. The derivative of that is going to be 1/2 root x dx. So essentially this 1/2 is a 1/2. So I need to introduce a 1/2, so I'm going to balance with a 2. So this becomes 2 times the integral of e to the u du. I replace this with my du and my square root of x with u. Anti-derive e to the u, that is e to the u plus c. And then I'm going to substitute that back in. I get 2e to the square root of x plus c, and there's my antiderivative. Okay, I'm going to come back with a video to show you how to do u substitutions when we have a defined integral and what that looks like. And then we're going to talk about odd and even functions. Take a look, continue. If you got questions, let me know. See ya later.